The lesson notes within this module provide examples regarding short-term forecasting, which is basically the moving average, right? The five-term moving average as highlighted in my slides, and a time series analysis, or rather just a basic regression, right? Where we factor in for time. So what I want to do now is just take a few moments to kind of walk you through the regression component, because the regression can be a bit more difficult to understand. It's not hard, but it can be a little complex, whereas the moving average is straightforward. It's just an average. Okay, so I want to spend time on understanding the regression. So why are we doing a regression, okay, instead of doing the five-term moving average? Well, as you'll see in my next video, when I actually open up a spreadsheet and show you all how to calculate these things in Excel, you'll notice the short-term moving average will have high, or rather steep, fluctuations in the data, okay? So when you want to do long-term analyses, right, you want to make sure that your data don't have as many short-term fluctuations in it. Like on this slide right here, you want kind of a steady trend going up or down over time, okay? Because if you think about it, right, like the stock market, for example, over time, over a 20-year period, the stock market tends to trend steadily upward. But if you go and look at short-term trends within that 20-year period, you'll see sharp and steep fluctuations. Okay, so you don't want to go by that, right? You want to go by the long-term trends. That's okay. Again, using moving averages to sort through short-term fluctuations. But when we want to get a long-term picture of something, you want to make sure that your trends are more even, if you will. Okay, so the first thing we need to do, as I said on my slide here, is to observe the data to make sure there were no short-term fluctuations. And as we can see with the city utility data, we don't have any short-term fluctuations, right? It's steadily moving up. Okay. So now that we know that the data are moving up, so now we need to go ahead and move forward with our analysis, our regression analysis. So since we are factoring in time, right? You see we have years here, 1992 through 2005, okay? We have to basically turn that year into an observable factor. So you'll notice here that I've numbered my years 1 through 14. So 1 stands for 1992, whereas 14 stands for 2005 is represented by 14, okay? Now, my dependent variable in this situation is city utility revenue, which is Y. So X is my independent variable, right? And Y is my dependent variable. So what I'm trying to do is I'm trying to see if time, right, increases in time have an effect on changes in revenue. And that's what this regression is going to tell us. All right, so now the steps in actually calculating the regression. So first of all, we have to calculate the means for X and Y. Okay, so when you see a bar over the X and a bar over the Y, that basically, in statistics, that stands for the mean of X and the mean of Y. So the mean of X in this scenario is 7.5, and the mean of Y in this scenario is 48.3. So my Y observations, again, are my utility data, and my X observations include my years, or rather my numerical representation of my years. Okay. So now the next step would be to subtract the respective means from each instance, or I in parentheses, of X and Y. Okay. So you notice on my little table here, I have X of I minus the mean of X, right, and I have Y sub I minus the mean of Y. That basically means I need to take each instance of X and each instance of Y and subtract the mean from them respectively. Once you do that, for all of your values, all of your instances, right, then you want to multiply the differences in Y by the differences in X. Okay, as you can see here, X sub I minus the mean of X times Y sub I minus the mean of Y. Okay. Step 4, you're going to sum these things together, right? Remember, in a prior video, I talked about when you see the sigma, that basically means you need to add a bunch of things together. So that's what we're going to do now. So once you multiply those differences together, right, then you want to add everything up, okay? So the sum of all my data from 1992 through 2005 comes to 392.5, okay? And I'll show you that on the spreadsheet in another video, in my next video actually. So now we're going to square the differences in the independent variable, right, and in the dependent variables, okay? So then we're going to sum the squared differences for x, all right? So, and then of course I have my sigma, right? So this is x of I minus the mean squared, which equals 227.5, right? And that's the sum of all my data. And now we're going to calculate the slope and the intercept, okay? So the slope basically is going to represent the direction where my line goes. So basically, if there's a positive influence between my independent and my dependent variable, that basically means as my time increases, my revenue will increase. Okay, if there's a negative relationship or negative slope, that basically means that as my time increases, my revenue would decrease. Okay, so we're going to calculate the slope. So slope is represented by beta, so it's going to be the sum of x of I minus the mean of x times y sub I minus the mean of y, right? Divided by the sum of x of I minus the mean of x squared, okay? And that gives me a slope of 1.73, okay? Now my intercept is going to be the mean of y minus beta times the mean of x, okay? And so the intercept basically is where the slope on a xy axis touches the line at 0. Okay, so in other words, that basically means if no variables, right, were to affect if no independent variables were to affect my dependent variable would be a given number. So in this situation, right, when we take the 48.63 minus 1.73 times 7.5, that equals 35.66, right? So that basically means that all things being equal, right, if nothing were to change, my my intercept would be 35.66. So then we use that to do our regression. So now we have y hat. Okay, so y hat basically means a change in y. So a change in y basically equals the intercept plus beta times x. Okay, and this is our formula. So basically what we will do is we will apply this formula to every number in our data. So we would take the 35.66 plus the 1.73 times x, right? And that will give us an estimate of what x would be for a given instance, okay? So if we want to estimate what 2006 would be, right, we will basically take the 35.66 plus 1.73 times 15, which is year 15, okay? And so therefore 2006 revenue would be 61.6. And then we would do this for the remaining years. If we want to go figure out the next 4 years, we would estimate what 2006 through 2010 would be, right? And we would have fairly accurate estimates of what that revenue would be, okay? So if you have huge spikes in your data or you have outliers, right? I'm going to skip forward here. If you have outliers in your data, right, you want to account for that, right? You don't want to just run a regression analysis because what happens is regression analyses with outliers will basically skew your data, okay? So what you want to do, right, when you notice you have outliers in your data, right, you want to use an exponential trend analysis, right? That basically means a regression where you're using the exponent of a given number for that number, right? So in my example right here, right, I have 1,000. So I don't want to use number 1,000 as my number that I'm analyzing, but rather I'm going to use the natural log function of 1,000. And so the natural log function of 1,000 basically is 3, okay? Because 10 times 10 times 10, which equals 10 to the third power, which equals 1,000, right? The natural log of 1,000 is 3. So then, therefore, I would use 3, which is called the log of 3, okay? And we use that simply to standardize our numbers. So instead of me having numbers that vary by hundreds or even thousands of units, right? When you use a log of a number, right, that number has now been reduced such that now they only vary by, maybe 1/10 or a tenth of a decimal point. Okay, so just to kind of, for brevity, I just want to say when you're doing an exponential component of an analysis or a regression analysis, right, you want to use that log number so that you can have more standardized numbers and you can get rid of those outliers.